Hi, good evening, everyone. I want to welcome you to the Stephen J. Gould Prize Award Lecture. As chair of the committee, it is really a sincere pleasure to be here this evening to introduce the awardee this year. For more than 2 decades, Carl Zimmer has written about many topics in science, but he's especially known for his writings about evolutionary biology. Carl has authored, co-authored, or edited 13 books aimed at communicating the thrill and relevance of evolution, biology, and medicine. More recently, Carl has extended his audience to include college students authoring a textbook, a popular non-majors textbook, The Tangled Bank, as well as co-authoring a book with Doug Emlin titled Evolution Making Sense of Life. So Carl has also been recognized by various awards, including AAAS's Journalist Award and the National Association of Biology Teachers Distinguished Service Award. So it really is an honor for the Society for the Study of Evolution tonight to provide this, to present this award to Carl. So I'm going to ask Carl to come up, and we have a special award here. So the Society for the Study of Evolution awards the Stephen J. Gould Prize in recognition of sustained and exemplary efforts to advance public understanding of evolutionary science. So thank you, Carl. So Carl's lecture tonight, Surviving the Branch, How Genomes Are Revealing the Twisted Course of Human Evolution, I think we'll all enjoy that. And then at the end, we'll have time for questions, and there will be microphones out in the audience for you to use. So thanks, Carl. Congratulations.
Thank you, Louise. I'd like to thank the Society for this great honor. It means a lot to me to receive this award and to be able to talk to you today. It means a lot to me for a few different reasons. For one thing, I feel like, can I get my slides? There you go, thank you. So one reason it's a great honor is it's incredible company to be in. People like Sean Carroll and David Quammen and Ken Miller, I've sort of privately appointed as my personal gurus about writing about evolution and communicating about evolution. And if you haven't read these 3 books, Endless Forms, Most Beautiful, Song of the Dodo, Finding Darwin's God, I highly recommend it. You're in for a real treat. Now, of course, the other reason it's a great honor is because of the person it's named after. Stephen J. Gould was extraordinary both as a scientist and as a writer. As a scientist, he was really a kind of a fire hose of new ideas. Some of those ideas didn't work out. Some of them sort of fizzled away, but there were a lot of them that proved incredibly influential and thought-provoking. And so I'm sure that there'll be a number of scientists presenting research at this meeting who may feel like Gould is there sort of standing behind their shoulder, kind of looking at the work that he helped inspire. As a writer, and speaking as a writer, I really feel that Gould was one of the masters of the modern essay. He did with essays the kind of thing that all writers are trying to do. He had a voice. You always knew who you were reading when you read something by Stephen J. Gould, whether it was an essay in natural history or one of his book-length works like Wonderful Life. Even if he was showing up on some Sunday morning news show, Gould had a distinctive way of talking about the world and ideas that he wanted to convey. And as a writer, one thing that was really important about him is that he didn't just trudge through some new piece of research. He didn't throw out the cliches that everybody uses. He didn't draw shallow conclusions. These are some of the pitfalls of science writing, I think, and he didn't make those mistakes. He had a knack for finding a subject that you didn't know about, some obscure geologist or some species of barnacle, and then he would write about it, and he would make you care about it. He would make you remember that barnacle. And then sometimes he would write about things that you thought you knew about, like maybe the Scopes evolution trial. But he would dig down and actually show you things about it that didn't fit your kind of received notion about it, the things that you heard secondhand. And he would really get to the core and show you things that really mattered and make you realize you didn't really understand it at all. And I think that was a real knack that Gould had overall to keep stressing that it's really easy for us to make mistakes, to fall into error, and to be seduced by ideas and ways of looking at things that seem like they should be true. And a lot of times that involves kind of flattering ourselves, either as individuals or as a species. And he was always warning us not to make that mistake and to really kind of try to look at things and try to figure out how they really are. I started reading Stephen Jay Gould around the time that this cover came out in the early 80s. This is a 1982 cover. So Stephen Jay Gould was in his early 40s. He was, one of the best known scientists in the country by then. I was in high school, I guess. Gould had sort of gotten to this point, having grown up in Brooklyn and fallen in love with evolution by going to the American Museum of Natural History, looking at the fossils. And then he had gone on to get a PhD at Columbia, specializing in the fossils of land snails from Bermuda. I only discovered that kind of later on, and I was always sort of amazed, because doesn't really sort of sound like the kind of raw material to build a career as like one of the country's best known scientists. But he loved those land snails, and he also sort of looked at them and thought about really big issues about life in general, which he would then extend to other species. And he had a lot of big questions. He wanted to know like what about the tempo of evolution. He wanted to know, how do new forms of life emerge? He was really emphatic about life not being a sort of a simple march of progress. One of his most famous ideas with Niles Eldredge was punctuated equilibria, the idea that actually evolution could go through bursts and then periods of stasis. One of the reasons that this dinosaur was on the cover with him is because not long beforehand, there was evidence that a giant asteroid had smashed into the Earth and may have played a big part in the extinction of big dinosaurs and lots of other species. And Gould really emphasized, that was not planned. That just happened, and mammals happen to be good at surviving those sort of conditions, and so now we're here, and these big dinosaurs aren't. So he really emphasized, that we are lucky. So I started reading his essays. Just I wasn't planning on being a scientist, and so I wasn't looking at his original papers. I was just really enjoying his writing. Myself, I wanted to write something. I wasn't really sure exactly what. So I went to college, studied English, took science classes because I was just enjoyed them, but I really didn't put them together. And it was a couple years out of college when I happened to get a job as an assistant copy editor at a science magazine, at Discover Magazine. So, that sort of luck and contingency that Gould was always talking about certainly played out in my life. I was just very lucky that somebody happened to look at my letter and say, why don't you bring him in to take a test? That was a great opportunity for me to learn how to become a science writer. And actually, I started gravitating towards writing about things having to do with evolution, thanks in part to Gould. And it was actually working at Discover that I was able to meet Stephen Jay Gould once. I met him once in my life. The opportunity arose because I was starting to edit pieces in the magazine, and he had written an essay for Discover, and somebody thought that it would be okay if I edited him. I was 27. And so I thought, okay, I'm going to just pick my battles here. I'm going to maybe make a few suggestions about word choice and punctuation. And that, I have to tell you, that was one of the toughest phone calls I've ever had. And I think, as I recall, I managed to get him to change one comma. And when I heard him say, fine, on the phone, I just felt such a feeling of victory. And that's just how he was. So fortunately, that did not burn any bridges. I was actually able to write him a letter later on, back when we actually wrote letters. And I asked him if I could pay him a visit because I wanted to ask him some questions about big transitions in evolution, his thoughts about it. Because I was working on a book, my first book, At the Water's Edge. And that was about life coming on land and life going in the water. And of course, Gould was already there. He had already written about those things. And so I just wanted to talk to him and just get some ideas. And I had a whole bunch of questions laid out. And I went to his apartment, and I was directed to his library. And I'm sitting there, and I've got my questions ready to go. I don't know if I actually managed to ask any of them, because he started immediately explaining to me about some, at the time, to me, very obscure 19th century Swedish paleontologists that I had to know about. And I think he actually had like one of their original monographs, which he sort of handed to me to look at, not to take, and just saying, you have to start there. And he was right. These were some of the people who first started figuring out which were the fish that actually came on land. And his point there, I think, looking back, was like, history really matters. I'm a journalist. I tend to think about things happening right now. What's the latest news? But, people like Gould are really valuable to remind you of the importance of history in something like science. Gould died of cancer in 2002. Shortly before then, he stopped writing his column in Natural History. It was a really great privilege for me to be asked by the editors there at the magazine to continue to write about evolution there. So I got to have that experience of writing essays about evolution. I was not going to try to write about Mickey Mouse and baseball and all the rest of things that Gould wrote about. I said, okay, what am I going to do? And I feel like I'm more of a journalist, and so what I was going to write about was going to be the big advances in understanding who we are and how we got here. How did humans evolve? And at the time, in the early 2000s, things were really changing dramatically in terms of how we could study that. And it's been my privilege to be following that story the past 15 years or so. Now as a columnist at the New York Times, and things have just changed in a really remarkable way. And so I just want to kind of give you a sense of what I've been able to observe in terms of how we're changing, how we understand who we are. I mean, this is a question that Darwin himself was really very obsessed with himself. Ever since he started working on his theory of evolution, he just didn't really talk to many people about it. But nevertheless, I mean, he recognized that if his theory of evolution was right, if species had evolved, we were not any different. We were not exempt. That was something that he saw very clearly. And so, he knew that Linnaeus had classified us as primates along with monkeys and apes. He saw that as a sign of common ancestry. Apes, like us, don't have tails. That suggested that they are more closely related to us than monkeys are to us. It's not easy. It wasn't easy for him to be a human evolutionary biologist in the early 1800s. I mean, people didn't really know how to study apes scientifically in the wild. Nobody knew about DNA, all the rest. So he did whatever he could. So, for example, he famously went into a cage with a baby orangutan when it showed up in the London Zoo. This was a really rare opportunity to actually see an ape. And he was a very careful observer. He would watch, was an ape, an orangutan called Jenny, and he watched her play with a stick, use it as kind of a lever. She looked at a mirror, kind of put her hand behind it, made faces in the mirror, and he was noting all these things and thinking about what did that mean about what Jenny and we have in common. And this is all happening in 1838, which is an incredibly early time when you think about it, to be having these thoughts. But he kept those thoughts pretty much to himself. He wrote letters to friends, but this wasn't something he was going to be airing publicly. And if you read The Origin of Species, it's really amazing how little he says about humans there. There's really only one line, this famous line, "Light will be thrown on the origin of man and his history." That's it. Doesn't tell you what kind of light. He just promises you, trust me, this will be important. And he kept thinking about humans, but again, it still wasn't easy even after The Origin of Species came out. And one of the big problems was that there weren't a whole lot of fossils for him to look at. In fact, there were hardly any, and some of those fossils people just didn't know what to make of. So, for example, in 1864, just 5 years after Darwin publishes The Origin of Species, some quarry workers in Germany dig up this skull cap and some bones, and scientists are puzzling over this. What is this? It looks human, but that brow, that slope of that skull just looks kind of weird. Is this human, or maybe is this another species? This was found in the Neander Valley, and so it came to be known as Neanderthal, tall meaning valley. Thomas Huxley, who was Darwin's friend and great defender, he looked at the skull and decided, I think this is human. And it was a little shocking. He admitted that you could have people in Germany who had this brooding, primitive kind of look, but he assured people that people in Europe, a few thousand years ago were all barbarians, and this Neanderthal would have fit right in. He has this great line. He says, "Even of the Germans, Caesar remarks that the Roman soldiers were unable to withstand their aspect and the flashing of their eyes, and that a sudden panic seized his army." So, Huxley was imagining some army of Neanderthals bearing down on the Romans. So this is basically it for the fossil record of humans in Darwin's time. And, a few other things that people are also puzzling over. That didn't stop Darwin. This is actually a tree from 1868 that he drew in a notebook, never published, but you can see on the upper left-hand corner there, man. So again, he sees us as a branch on that primate tree. In 1871, he published The Descent of Man, where he actually presented a lot of the ideas he'd been thinking about for years and years and years. It's a huge book. It's kind of an odd book. We could talk a lot about it, but the only things I really wanted to talk about tonight were just a couple of key things that he proposed about human evolution. So he proposed that we started out as apes, as not walking upright, walking around on all fours. He then argued that we then stood up, that freed our hands, we became tool makers, and our brains evolved to become more powerful. So there was just a sort of series of events that he was laying out, kind of a plausible scenario based on all the evidence that he presents in his book. So it turns out that in some ways he was remarkably right. There were some things he got really wrong, but again, that's okay. It wasn't really until well after his death that some of the first fossils emerged that really started to show what human evolution was really like. So in 1924, Raymond Dart describes the skull of a child that has this interesting mix of traits. It's got a small brain, kind of ape-like. It's got small teeth, though. It doesn't have the huge teeth you'd find in a chimpanzee. It's this mixture that Darwin would have predicted. So some traits that are human, and then some traits that seem to be like other primates. This, of course, became Australopithecus africanus. Turns out to be about 2.8 million years old. And this is a reconstruction at the Smithsonian of what it might have looked like. What's been really exciting as a journalist is to sort of be keeping up with a lot of the discoveries that have come actually quite recently. I mean, Dart found this, described this in 24. You know, every couple decades there was a pretty exciting fossil, but now things are coming out pretty fast, and it's pretty remarkable. In the early 2000s, actually the oldest known and perhaps the most primitive of these ancient human relatives, hominins, was found. Oldest known so far, Sahelanthropus, found in Chad. And so as these new fossils emerge, you know, it's very tempting to just sort of array them in your mind and say, okay, well, we started as Sahelanthropus, and then we were Australopithecus africanus, and then here we are, right? This is just that classic way of thinking about human evolution as just a simple march of progress. You know, we're better than what came before, so you start with these lowly apes, and then you get this sort of halfway human, and then here we are. And so it's a very linear thing. And this is something we see over and over again. This is like a very powerful, appealing image. I mean, how many times have you seen this in one form or another? But it's just not how evolution works. And this was something that Gould was relentless on in his public writing about science, that, you know, evolution doesn't work in some simple march of progress. And it's still an easy thing to forget. It's easy for the public to forget. It's easy for journalists to forget. And sometimes even scientists forget it sometimes. It's not necessarily how things go. And so if you actually look at a chart of where you look at all of the hominid fossils that we found so far, you know, you really don't see that march of progress. This is actually just came out earlier this year. It's from Bernard Wood and one of his students. And this is just about all the known hominins. You know, whether some of them are separate species or not, you know, we'll leave that to the paleoanthropologists to argue about, and they will argue. But it gives you a sense of the diversity of hominins that have been around just from what we've found. You know, this is just the fossil record, and just people going out to places like the Sahara or Odelite Gorge or South Africa in a cave and just dragging up stuff. This is all we know about, but it's still, you can see that there were a lot of different hominins, and there were a lot that were living at the same time. Before 2 million years ago, you know, all these hominins are found in Africa. So for that first 5 million years or so, you know, hominins are evolving in Africa, and they're evolving to several different kinds. And, you know, each species might last for, say, 1 million years. It might, in that time, you know, give rise to a new species, and then it's gone. And that is happening over and over and over again. So I'm reminded when I look at this chart of something that Gould wrote actually in 1977, almost 40 years ago, when actually many fewer of these fossils were known. He wrote, "Homo sapiens is not the foreordained product of a ladder that was reaching towards our exalted estate from the start. We are merely the surviving branch of a once luxuriant bush." I apologize, I left the A out. But the point is that, you know, that you know, we are the last one. That's it. But there was a lot more company before. So scientists have been taking that chart and trying to figure out how those species are related to each other. They're trying to draw the kind of tree that Darwin wanted to draw for humans, particularly for hominins. And this is a recent one from 2015 from David Straight at the University of Albany and his colleagues. And as you can see, I mean, Straight is trying to present human evolution as he sees it, but also trying to be a bit humble with some dashed lines and some question marks, because there are a lot of situations where either we don't have a lot of fossil material, or we've got some fossil material and it's kind of confusing, because a lot of traits that you see in one hominin may have evolved in another one, which always makes these trees kind of hard to put together. But this is this is sort of our you can consider this one of our current hypotheses for how humans evolved, taking into account most of the fossils I showed you. And what's interesting is you can look at that and you can ask about those basic points in Darwin's story of how we evolved. So he was very interested in, for example, how we started to walk upright. And actually, if you look at the oldest hominins, you see some really interesting evidence that we probably were able to at least kind of walk upright. So for example, here's Orin, which is around 6 million years ago. This is all we've got of it. Not a lot, but enough to make some inferences. Those femurs, those thigh bones, are really telling because of the shape of that ball. The angle of it gives you some clues about how that hominin was using it. And it looks like this is a kind of a femur that you could use to stand upright and to walk. Maybe not all the time, maybe not all that well, but it's different from something that was on all fours and had to stay on all fours all the time. If we jump forward a little bit to, about 5.5 million years ago, here's a species called Ardipithecus from Ethiopia, which was found in the 1990s, but only recently has a lot of information about it come out, but it's, it was worth the wait. This is quite a skeleton, and it potentially tells you a whole lot about all sorts of things, including how it moved around. And again, this is a reconstruction, a plausible reconstruction based on the skeleton. This is another biped. But again, very long arms, long hands. These legs probably weren't that great for walking around, as far as we can tell just from looking from these fossils. If we go forward to about 3.5 million years ago, we're already about halfway through hominin evolution now. That's something to sort of bear in mind, is that these things I'm showing you, these just totally dominated hominin evolution for a long time. And so we have now, what's shown here is Preanthropus afarensis. You may know it as Australopithecus afarensis, or as Lucy, after one of its skeletons. This is what it looked like, roughly 3.5 million years ago. And because we have so much skeletal material of this, we actually know a lot about how this particular hominin walked around. We even have walkways we can look at, which were made at the time and the place when afarensis was hanging around. And scientists have actually made these sort of 3D models of those tracks and kind of calculated, well, what kind of forces would you need given what we know about the skeleton? And this looks like how they might be walking. Not very well, not very efficiently, couldn't run, but it was enough to get around. And that may have been ecologically very important. Nevertheless, they still were probably, good tree climbers. And so what you have is bipedalism coming on very early, but not really becoming sort of the bipedalism that we know that lets us, run a marathon, if you can run a marathon, unlike me, and also very small brains. These are hominins that have brains like a chimpanzee, basically. And so it's not quite, these components of what Darwin was talking about are really important, but they're not quite lining up the way Darwin had laid out. What's really interesting is really, just in the past few years, scientists have been digging up some other very interesting things from these sorts of places. So in Kenya, at this site called Lomekwe 3, they're digging, and they're as you can see, they found something. They're scraping it away. It might look like a skull, but actually no, it's actually a rock. But it's a really interesting rock. It is actually a tool. So these are 3.3 million years old. They've only been found in the past few years. This pushes the date of the oldest tool making way back. These are actually tools. These are things you have to make. You have to take one stone and bang another stone. You have to make in order to make an edge on it. This is something that hominins might have been using to scrape off meat from carcasses, or maybe cracking open bones to get at the marrow. They were doing this really early. And this is something that seems to be pretty distinct from our closest living relatives. Chimpanzees can make tools. So can orangutans. They're pretty good at it, but this kind of stone technology, they don't really have it the way that hominins had it. I mean, they can use a stone and bang some nuts or something like that, but the kind of stone tools that scientists dig up from hominins, not in our relatives. And so it's these bipedal apes, maybe 3.5 million years ago, that are starting to make them. And that scientists are actually trying to understand what happened in their brains to make that possible at that particular time. I mean, how did this come about? We don't know who made them. They weren't found near fossils. I mean, we can say we know there's a certain period of time in this part of Africa. It's potentially one of these species, or maybe one we don't know of. Maybe stone tools were invented more than once, and maybe that technology was lost by some species that went extinct, but it was carried on by others. We just don't know. But we do have a new kind of marker we can put down in the history of our lineage. We know that stone tools were being made 3.3 million years ago. So between about 3.5 million years ago and 2 million years ago, you continue to have this brilliant evolution of different kinds of hominins. Some kinds like Paranthropus, where you had some species with huge jaws, just these, using maybe to grind up really tough plants or something. There's a lot of diversity, but around 2 million years ago, roughly, we start to see our own genus starting to really come online. The first ones that we're going to call Homo, particularly Homo erectus, which is about 1.8 million years ago that we find them. They were tall, as tall as me. They had bigger brains than before, about 2/3 as big as ours. And if you look at their anatomy, I mean, not only are they tall, but their anatomy is really adapted for walking. They're committed to the ground. They're not going to be that good at climbing trees, and they could probably even run. According to Dan Lieberman at Harvard and his colleagues, they actually had a lot of adaptations that might have been for running. Like, for example, the nuchal ligament that actually hold your head steady while you're running. Imagine running and not being able to hold your head steady. That would be a problem. Earlier hominids didn't have that, as far as Dan Lieberman can tell. So we have this adaptation in this particular branch of hominins to moving around on the ground, moving efficiently, moving quickly, maybe moving to get to some food, maybe getting to a carcass before other scavengers get to it. And they're making new tools. So for example, this is a hand axe, these magnificent giant stone tools that they're shaped on both sides. And so, you're really looking, now you're really starting to see a very interesting looking hominin. And perhaps not coincidentally, these are the kinds of hominins that are moving out. They are expanding out of Africa for the first time. They're going to Europe, they're going to Asia, and they are perhaps using fire as part of the ways that they're making their way through the old world. And they're staying at a lot of those places for quite a long time, until quite recently. But Homo erectus, no matter how far it went, it's gone. It is another one of these species that became extinct. It's hard to know why they became extinct, and maybe one kind of clue we can get to sort of think about this is to look at their technology. I mean, how were they making their way in the world? And what's really amazing is if you look at those axes I was telling you about. So the first two are 1.75 million years old. So there, what you're seeing is the top left-hand corner, you're looking at one side of a hand axe, and then the bottom left-hand corner, it's the other side. And then there's another one right next to it, the two sides. So those are 1.75 million years old. You see the kind of style they're using on that. And you see the ones next to it, and they seem like pretty much the same. Well, yeah, but they're 150,000 years more recent. These are 1.25 million years old. These are 850,000 years old. So we're almost a million years here at one particular site. And, you know, nothing's changed. This is not your iPhone getting updated every year, to say the least. And so, you know, like innovation, creativity, looking at materials and thinking about new ways of using them, this is not in Homo erectus's playbook. Now, you know, Gould will remind us, like, look, just because they're not like us doesn't mean that they didn't do pretty well as a species. They did fine. They were around for, you know, 1.5 million years at least. That's pretty good for a hominin species. We'll see how we do. And so, you know, if we want to really see the first, you know, glimmers of what we would think about as maybe creativity, of innovation, of expression maybe, we actually have to get to the past maybe a couple 100,000 years, and we have to look at our species and Neanderthals. Now, you know, you might say, like, why is he talking about Neanderthals? Isn't that kind of an insult? When you want to call someone stupid or an idiot or a savage, you call them a Neanderthal, right? Well, this is one of the things that has really changed recently in a lot of different ways, is that we're developing a very different idea about Neanderthals than we had 10 or 20 years ago even. That sort of reputation of Neanderthals as a brute was really locked in the early 1900s as more bones emerged, and there were these reconstructions like this one in 1909 of a hairy ape, basically, like really kind of an upright gorilla almost. And what that overlooked was that, you know, these Neanderthals, they had big brains, in some cases bigger than ours. So just because they might have some big brow doesn't necessarily mean that they were stupid, that they were even, you know, covered in hair like a gorilla or something. They were part of a trend in, you know, increase in brain size, you know, that we enjoy as well, that comes at the end of several million years of evolution. And so when Neanderthals emerge in the past, you know, few 100,000 years, they emerge with the kind of brain size that we have. And so we start to gain an appreciation now of Neanderthals as being tough and resourceful, as being able to thrive in a wide range of the old world, all the way from Siberia to Spain, you know, enduring ice ages, you know, glaciers moving in and out. And part of the reason they were able to do so well was because they were able to make better tools. I mean, if you look at their tools compared to Homo erectus, they're far superior. They were probably using them for lots of different things, like butchering and cleaning hides and fashioning clothes. And, you know, these kind of tools were, you know, they were on par with what our ancestors were making, you know, 150,000 years ago, say. And, you know, if you look at these tools and think about how they're being used, you start to see Neanderthals as, you know, able to make some of these tools and put them on the ends of sticks and use them as spears. So these were incredibly sophisticated hunters, able to take down huge game. But then there was the kind of the softer side of the Neanderthal. They would, for example, make they would use shells and put ochre on them, and this seems to have a drill mark on it, so you could imagine this might be some sort of pendant. I personally prefer the eagle talon necklace, which was actually just found and described last year. This appears to be something where these talons were collected and probably used as some sort of ornamentation. Just a couple weeks ago, French scientists described a cave where it appears that Neanderthals would go deep into this cave about 160,000 years ago, and they would take stalagmites that were in the cave, they would break them off and haul them around and create circle-like shapes, big circle-like shapes. We have no idea what they were using them for, but you can't help but think, was this some sort of sacred site for them? Was this kind of like a Stonehenge for them? We don't know, but I think if you just look at something like that alone, that makes you think about Neanderthals in a different way. And these would have been Neanderthals because modern humans were not in France until about well over 100,000 years after these caves. So, we're looking here at a different kind of Neanderthal, and one that also shared the planet with us. Meanwhile, back in Africa, our species was evolving at the same time. When I say our species, I just mean like modern humans. I mean, I'm always trying to ask scientists who study Neanderthals, so are they a separate species or not? And they always say, like, I really don't want to talk about that. Like, they don't want to, the whole species question is always such a nightmare, and it's particularly one for humans and Neanderthals. So basically, what we'll call modern humans, they evolved in Africa. The oldest fossils that really seem to look like us are about 200,000 years old. And this one is 160,000 years in Ethiopia. And with us, you also see kind of an efflorescence of creativity. You see shells, again, that might have been used as necklaces, maybe a way to identify yourself as part of a group or having some particular status. You see ostrich eggshells with geometrical patterns on them. And then it continues in a way that we don't really see with Neanderthals. So that by 40,000 years ago, you're seeing rock art, you're seeing sculptures, and so on. But again, I don't want to give you the impression that we're again watching some sort of march of progress. We're seeing a tree branching in all sorts of interesting ways. So Neanderthals and humans simultaneously were developing these sorts of traits, these signs of innovation, of tool use, of expression, and so on. This was happening in two different branches of humanity. And really, like, if you want to really dash that sort of image of some sort of simple march of progress, you just need to look at this particular species, Homo floresiensis. Maybe the most interesting hominin of all. I mean, maybe I'm biased. I wrote about this recently in the New York Times, the most recent research on this particular species. It appears to be a hominin that stood about 3 feet tall with a very small brain. Its ancestors came to the Indonesian island of Flores probably about 1 million years ago. And they brought tools with them. This was probably Homo erectus, so as tall as us, came to Flores, and the evidence suggested then shrank. So by about 700,000 years ago, it looks like it was already about that small. And that may have been just an adaptation to that particular island. And they shrank that brain down too, but they were still able to make those Homo erectus style tools. So this one species raises all sorts of questions for us about what it means to be sort of man the tool maker. You can shrink a brain right back down to incredibly small sizes and still have a hominin that can make tools. So maybe it's not about the size. Maybe it's more about how brains are organized. We don't know. But we might be able to get some more answers to these kinds of questions from a source of evidence that Darwin couldn't even imagine, and which has only become available recently, and that's DNA. So DNA, just to remind you, is is written in this alphabet, basically of 4 letters, and so it's kind of like a cookbook where genes are made, consist of thousands of these letters in a row, and they encode proteins and other molecules. You have about 3.5 billion bases in your genome. Someone recently decided to print out his genome, and he hauled it on stage, and so this is what it's like. So basically, you need to clear a big space on your bookshelf for your genome if you want to read it in really small type, by the way. So this is actually, for scientists, this is an unbelievably rich source of data. This is a historical record, and the reason is that you can look at 2 different individuals and look at where they're similar and where they're different. Just as you could say, look at a monkey and say, well, they've got opposable thumbs like us, but they've got a tail and we don't. You can look for differences, and there are just a whole lot of differences that you can potentially have. Now, it just so happens that there's one difference in these 2 strings of DNA. The top one comes from humans, the bottom one comes from chimpanzees. So we're genetically, there's a lot of similarity between us and chimpanzees, and so in recent years, scientists have been able to show that the DNA confirms what Darwin was claiming from anatomy, what others were arguing from other evidence like fossils. So we are apes. Chimpanzees and bonobos are our closest relatives. These things are brought out now by DNA in the past couple decades. And DNA, if you look at the mutations in different species, you can actually get a rough idea of the timing. So these sort of blurry branches give you a sense of the possible ranges when these branches may have split off. And you can see it kind of lines up pretty well with the fossil record. There probably are older hominins waiting to be found if this tree is correct. But that's not surprising, given that, say, Sahelanthropus, for example, was only found in around 2001. There's got to be a lot more fossils in the ground waiting to be found. But that's just if you look at the DNA of living people and living primates. And one of the real privileges that I've had as a journalist is that I started writing about ancient DNA back when really the only place to read about it was in Jurassic Park, and we all sort of thought it was probably just totally bogus. There were claims that people had found dinosaur DNA, and that just turned out actually to be human contamination, actually. But after a while, people like Svante Pääbo were able to show that, yes, indeed, you can get ancient DNA out of fossils going back tens of thousands, even hundreds of thousands of years. There's a horse where scientists were able to get 700,000-year-old DNA out of it just a few months ago. Well, Pääbo has been particularly interested in humans and our relatives, and so he went back to the classic stuff. He went back to that skull cap of the Neanderthal and went to other Neanderthal material, was able to get some DNA out of it, and the more DNA he could get out of it, the more he could draw that Neanderthal tree with genetics. And so, what he did was he showed that, yes, indeed, we are a separate branch. We're closely related to Neanderthals, closer than chimpanzees, but they're a separate branch. And he and his colleagues date that to about 600,000 years ago. You can try to start making some inferences about what they look like from their mutations in their genes. So if you look at genes they have for hair, it looks like they have mutations in a gene that controls hair color. So it's possible that they might have been red-headed Neanderthals, at least some. But they had a different mutation than the mutation that makes people like Lucille Ball red-headed. So Pääbo and his colleagues went looking for more material from these Neanderthals, for better material, because they wanted to do the whole genome. And the best place, it turned out, was actually a cave in Siberia called Denisova, where they found there's lots of material in there, stuff from humans, stuff from Neanderthals, just a lot of stuff in there. It's been occupied off and on for probably over 100,000 years. So they got a toe bone, actually, that had a whole Neanderthal genome in it, just loaded with DNA. What they didn't expect was that they were going to find fossils with other genomes in it. So this tooth turned out to have a little bit of DNA that didn't really line up very well with Neanderthals or humans. And they thought, what's going on? And then they found a pinky bone, which apparently comes from the same individual. And what they figured out was this was a separate lineage, most closely related to Neanderthals, probably split off maybe 400,000, 450,000 years ago. So they've named it Denisovans, after the cave. But we've got the whole genome, and then we got like a couple teeth and a pinky bone, and that's it. That's it. So if you want to say, well, what do they look like? Can you make me the skeleton? Well, I can tell you, well, it had teeth like that. And the scientists are trying to infer things from its genome, but we're in this very weird situation where there is an extinct hominin that we basically only know from a genome. And it's not going to be the last. I mean, it's becoming clear that there are going to be others like this. And what's really particularly exciting is that you can then use these genomes, our genome, a Neanderthal genome, a Denisovan genome, and you can look in those genes and say, all right, so what happened in human evolution on a molecular level? So for example, what were some of the genes involved in this big question of how our brains evolved from chimp brains into brains like ours? There are about 20 million differences, roughly speaking, between our genome and a chimpanzee genome. So that's a lot of possibilities to look at. Which one of those changes actually had anything to do with our brain? It's a hard thing to choose to figure out, but there are a few really promising candidates. So for example, there's a gene, it's called SRGAP2C. It doesn't really roll off the tongue, but it's a really interesting gene. It's interesting because we have it, Denisovans have it, or had it, Neanderthals had it, chimpanzees don't. In fact, no other species has it. And this is a gene that's active in the development of the brain. And so this is a very, very interesting brain. And so some scientists took a look at it, and what they figured out is that it actually is the result of a duplication of another gene, a similar gene, maybe in our common ancestor with chimpanzees. So you had one gene and it duplicated into two, and then this new one started to mutate and do interesting things. And so some scientists said, well, what would happen if we would take this new gene and insert it into mice, into mouse embryos? How would they develop? And spooky as it sounds, their brains started to develop kind of in interesting sort of human ways. I don't mean that they attended scientific meetings, but their neurons sort of stretched out as they were developing in a way that's more distinctive of humans than of mice. They grew lots of little projections, little spines on the side of them that are good for making connections. And also, the brain sort of kept developing in a sort of an infant kind of exuberance, the way that our brains does compared to, say, chimpanzees. So this could be potentially like one of these really interesting genes that maybe, say, a couple million years ago, it evolved, and then it led to some changes that are reflected in what we see not only in our fossil record, but in Neanderthals. And again, we're talking about hominins that have been gone for tens of thousands of years, or maybe not. This is an interesting list. It's actually very interesting to me personally, because these are genes actually from my own genome. I got my genome sequenced, and I had some scientists look at it. I'm writing about it for a series that's going to be appearing shortly in Stat. And I just thought I'd share with you these particular genes. This is a part of a list of 613 genes that are very interesting because of where I happen to get them from. These are Neanderthal genes. So if you've gotten, I don't know how many of you have gone to 23andMe and gotten tests to look at your ancestry from DNA. It's really amazing now that they can tell you, oh, you're like 2% Neanderthal or 2.1% Neanderthal. That's because it turns out that humans and Neanderthals interbred. When scientists look at the Neanderthal genome and then compare it to some humans outside of Africa, they see chunks of DNA that really match the Neanderthal DNA. They're different chunks, though, which is interesting. So my 2% might be different than some other non-Africans' 2%. And so what's really exciting is that scientists can actually break it down, and they can tell you, well, these actually are, this is your personal set of Neanderthal genes. So I'm walking around with 613 genes that I got from Neanderthals that were presumably evolved for being a Neanderthal, and they're in me. That, personally is very strange, but at least I take some comfort in knowing that lots of you probably have your own assortment. And it turns out that Neanderthals are not the only hominin that provided some DNA to living humans. So those Denisovans turn out to have actually left a substantial amount of DNA, a few percent, in people, for example, in New Guinea, which is kind of weird because they're known from Siberia. Scientists have found that in Tibet, Tibetans have a gene that helps them to survive at high altitudes, and that comes from Denisovans. They don't seem to have much more Denisovan DNA than that, but they held on to that. So things are getting. I know that Gould was, like to talk about this luxuriant bush of evolution. I don't think he quite reckoned on this. I don't even know what we call this. I don't know if you choose your word, a bramble, an orgy, whatever you want to call it. This is complicated, and this isn't the end of it. So what we have here, and this is just, this tree is the 2016 version of this tree. I'll say this tree is the early 2016 version of this tree, because I wouldn't be surprised if this fall it changes again and we add in another arrow. So the reason that I and other non-Africans have some Neanderthal DNA is that step number 2. But it turns out that actually early humans actually ended up giving some DNA to Neanderthals that ended up in their genome. Denisovans then gave some DNA to Asians and people in the Pacific. Neanderthals gave some DNA to Denisovans. And then there seems to be some DNA in Denisovan genes that doesn't come from any hominin genome that we really understand. It's some other hominin that's related to us, but dates back, I forget the exact number. Sorry, it's right there. It's over 1 million years ago. Could be Homo erectus. Again, this is just the start. There are probably hominins that were in Africa that interbred with Africans. There are studies that are suggesting that. So this is just the beginning of a new kind of tree. And it raises all sorts of interesting questions, just for starters, like, how did this happen? And where? So I mentioned, for example, Denisovans are in Siberia, and this chart, that's where that little star is. And yet, it looks like there was interbreeding in maybe South Asia, Southeast Asia. So does that mean that Denisovans were spread all over that range? Possibly, but we don't know Denisovans from anywhere else. Neanderthals. It seems that we may have encountered them in the Near East, but there seem to have been opportunities for interbreeding in other places. And like I said before, like Africa is left white there. This was done in 2012. I would argue that there should probably be some encounters there as well. So there's going to be a geography of human interbreeding that we're going to be learning about in the future. So we interbreed with these other kinds of humans, and some of their DNA ends up in us today, tens of thousands of years later. So there, what's interesting is that, some of them seem to be pretty valuable. So, for example, I can look at that list and I can identify, or rather scientists can identify for me, a number of genes involved in the immune system. So one possibility is that humans expand out of Africa, and not only do we come into a new landscape, but we come into a sort of a new germscape, a new world of diseases that we really haven't been exposed to before. Neanderthals have been there for quite a long time, and they have adapted. And so when there's interbreeding, those genes that are going to make humans survive these new diseases, maybe those are going to make them be able to have kids and pass down those genes. And so that's how I ended up with some of those genes. So a lot of you may have ended up with different immune system genes from those Neanderthals. There are lots of other strange genes. There's one that apparently puts me at risk of a higher risk of developing nosebleeds than average. And I don't know what that means. It doesn't necessarily have to mean anything. That's another thing to bear in mind, is that we can talk about adaptations in us. We can say like, oh, we have this gene because X, Y, Z, because it was favored by natural selection. That's possible, but that's not the only explanation. And that's something that Gould stressed, and that's something that's on a molecular level is important to bear in mind. So nevertheless, the fact is that we are here. We are the surviving branch. And so, the question is why? I mean, this is a planet that could support lots of different hominins at once, and many different kinds of hominins over evolutionary time. So why are we here, and why are the rest gone? Now, Gould would remind us, it could just be that we were lucky. It could be that Neanderthals experienced certain problems, and they were knocked out, and we just happened to be still around without any reason to pat ourselves on the back. Or it's possible that maybe we have some adaptations that actually helped us to survive in situations where Neanderthals in the end couldn't, or Denisovans. One of the possibilities is language, and there are some interesting studies going on about what kind of genes are involved with language, and how could those genes evolve to allow language to emerge. So the big one, the one that people really pay attention to, is FOXP2. It's a very powerful language gene in the sense that mutations to it can cause people to be unable to speak and to have difficulty with grammar. It clearly has something important to do with language, and you don't find our particular set of mutations in other species. It seems to have evolved very little in mammals. It's kind of locked in place, and it's probably involved in a lot of sort of motor control of various kinds. And we sort of adapted it to move our tongues and maybe to also do other things involved in language. And so scientists have been pinpointing certain mutations that we have that other species don't. So here are two of them. And so you could say aha, so this is what makes modern humans really successful. This is why we're here. This is why Neanderthals are gone, and that's great. But then what happens when you get a couple genomes to take a look at of other kinds of humans? Well, it turns out they had them too. So either that means that they had this gene that we think is really important for language. Does that mean they could speak too? Who knows? But what's intriguing is that there is one thing about FOXP2 that's different in us from even Neanderthals and Denisovans. It's another mutation, and this mutation, it doesn't change the shape of the protein, it doesn't really change what it does, but it seems to be involved in when that gene is switched on and switched off. So it has to do with the timing or maybe where it's expressed in the brain. And so maybe if you just take this FOXP2 and you just use it differently, maybe that's something that has something to do with, you know, what we think of as human nature, as me talking and you listening and you talking to each other. Like maybe that was a big change. And there's no question that language is a really powerful adaptation. It could have let our ancestors stay in groups better because we could talk things out. We could also plan things to, you know, attack another group, or maybe we could trade with them. We could share stories about, you know, what happened last time there was a drought. So I think that the molecular evolution of language is going to be an exciting thing to see in the future. That being said, you know, there's a long list of mutations that we have that Neanderthals and Denisovans don't. And you know, it's not an endless list. It's actually a finite list, which is amazing. We have a list now. And they're involved in all sorts of things. And you know, maybe they all had something to do with making us human. We don't know. And we're going to, as we, you know, discover more, you know, ancient hominins, maybe find more of their DNA, we're going to be able to dive into this even further. And you know, I'm really looking forward to be writing about all of this. I mean, that's one of the things that, you know, makes me excited about getting up in the morning and writing. Sometimes it's exasperating. A friend of mine, you know, emailed me about a paper that was just posted on a preprint server like last night about, you know, the DNA from the first farmers. And he said, "Are you going to put that in a talk? Are you going to write about that?" And I'm like, I don't have enough time. I don't have enough time to write about ancient DNA. There's too much ancient DNA out there. That's astonishing. I think Gould would be incredibly excited to be alive at this time and to have been able to see this. And I think as a pluralist, as someone who wanted us to think about a lot of different possible explanations, I think that he would urge us to not flatter ourselves as we look into our own genome and the genomes of other hominins, to think of all the different possibilities to explain why we're here, including maybe just dumb luck. So I'd like to thank you so much again for the prize and for spending some time with me to talk about these things that I'm so excited by. And I have time for questions. Thank you.